height. So let me now focus on this and think about how to find the relation. Okay, starting from the x. Right. The x value of this ball is just this. So that's the x value. So that's it, really. There's not. That's it for the x. Okay, not much else to say. The next thing we need to do is to think about the acceleration. Now, how would I be able to find the acceleration of this ball, or rather the acceleration of this point, this x, this height of the ball, right, as the ball goes round and round. Now, the first thing is that we can think about is this. We do know something about the acceleration of a ball in circular motion. We know that we know something called the centripetal acceleration. Now, a ball going round a circle must always be accelerating towards the center of the circle, right, if it is a constant speed. And this acceleration is called centripetal acceleration. Now I'll denote it by, I'll use the symbol AC to represent the centripetal acceleration, in order not to confuse with this A here, which is just acceleration along the x direction, right? Acceleration of this, the height of the ball, or rather the vertical component of the ball's acceleration, which is the idea that I'll need now. But for now, let me write down the formula that I know for the centripetal acceleration. It is equal to, well, one of the expressions is omega squared r, if you remember, where r is the distance of this circle. Okay, so for example, from there to there would be r. Okay, so I have that. Now that we have this, if I want to find the vertical acceleration of the ball, okay, the acceleration of the ball along this direction, all I need is to find the vertical components of this vector. So think of this as a vector, and we can resolve this component in two directions, the vertical and the horizontal. Okay, now to resolve this into vertical and horizontal direction, okay, let's see. What I'm going to do is this. I'm going to imagine moving this arrow to here. I'm going to move this arrow to here. So that's my centripetal acceleration. Now, I'm going to think about this component in this direction. So what I can do is I can draw a horizontal line here, right angle. So that gives me a right angled triangle here. Okay. Now then the other thing that I can do is I can compare this with this other triangle that I get from the x, from this line and this radius. This line and this radius. Okay, if you look at this triangle and if you look at this triangle, right, this right angle triangle and that right angle triangle, clearly they are similar triangles. Okay, this is along a straight line, so they are similar triangles. They're both right angle triangles. So therefore the vertical components of AC in this direction. Okay, let's see how we can get that. Now the relation between x and this length is this. This length is actually r. So the ratio between this length and this length is x is to r. Now I know what AC is. I know what this length is. I know if this is AC, I know that it is omega squared r. Okay, so this length here, let me just represent use the arrow to remind myself. So the AC here I know is omega squared r. Now this, therefore the vertical component, which is given by this side of the triangle. Okay, since the ratio of these two sides must also be x is to r, just like this side and this side. So if this side is omega squared r, so that side must be omega squared x. And you see, it now we now have this similarity. The vertical component here is omega squared x, and that also happens to be omega squared x. So therefore, the acceleration component of this centripetal acceleration along the x direction is actually omega squared x, and I can write it down now. I can write it down as the acceleration equals to omega squared x. So this is the acceleration in the x direction. Acceleration in the x direction. And the other thing I need to add is that the acceleration, as you can see, is in the opposite direction to the displacement. Displacement is up, that's x. Acceleration is down. Okay, so they are in the opposite direction. So therefore, to show this in the equation, I should have a minus sign to show that those two are in the opposite direction. So therefore, you can see now that I have shown that if this ball is going round in a circle, then the vertical displacement and the vertical component of its acceleration are indeed the same as the equation for are indeed the same as the equation for the simple harmonic motion. Okay. Right. So that means that I can actually follow the simple harmonic motion by following this vertical displacement of the ball going around in a circle. Right. So once we realize this, I can actually start making a formula for the x, and there's even some hope that I can arrive at that formula. So this is what I'm going to do now. Okay, let me try this. Okay, so how am I going to make a formula for this? Right, I want it in terms of t, right? I want it in terms of t. Now, let me start by thinking about an angle. About this angle theta. Yeah, about this angle theta. I know how theta is related to t. It's related to t by the angular velocity. So we know about this. We know about that omega is angular velocity is equal to angular displacement divided by t. So we know this relation. Okay, and if this length is r, we also know the relation between r and x and the vertical height. It is that x is equal to r sine theta. Okay, so that's the connection between r, x, and theta. And I can further write theta in terms of time, okay, because this gives, if I move t over to the other side, I get omega t is equal to theta. So r sine omega t. Now if you compare this with this, they are almost exactly the same, except that the a here is the r. So all I need to do is to rename the r as a. Okay, because I just made up a value for r, and if you compare this, it turns out that at the maximum displacement of the ball in the spring, this ball is also at the highest point in the circle. and the highest point is where x is equal to r, because I've called the radius of the circle r. So what this means is that the maximum displacement here, the a here, is indeed the same as the r. So therefore I can just say x is a sine omega. So by considering the physics of this problem, going around in a circle, centripetal acceleration, and comparing it with the simple harmonic motion, with the equation of the simple harmonic motion, okay, we have shown that they both agree, they both obey the same equation in the vertical, along the x direction, and therefore, since I can actually, from just by thinking about the circular motion, I can actually derive a formula for the x, for this vertical displacement in terms of the time and the angular velocity. This formula of x must also satisfy the same equation for the simple harmonic motion. So therefore, and since we have seen that the x displacement here is exactly the same as the x displacement here, therefore this formula would give the correct displacement in the simple harmonic motion.